All right, so today we are going to talk about how to work backwards in these problems. So let's read this one. This one says researchers believe 20% of all sea turtles have a shell over 2 feet wide. A researcher wants to use a sample of sea turtles in California to determine the sampling distribution of turtles with a shell over 2 feet wide. What is the minimum sample size of sea turtles needed for the researcher to make the sampling distribution? So it sounds like we are talking about a sample proportion. Here's how I know. It says researchers believe 20%. So we're talking about a proportion, right? And so in this case, we know that the true proportion P is 0.2 from that 20%, right? And it wants to know the minimum sample size that we need. So we need a normal model to be able to make this sampling distribution. And it's a sampling distribution for proportions. So we're talking about the large counts property. So in the large counts property, we need to know that we expect at least 10 that have a shell over 2 feet wide. And we need to expect that we have at least 10 that do not have a shell over 2 feet wide. So in this case, what I'm going to do is I'm going to say, okay, our true proportion is 0.2. And so I can find out what we need for both of these conditions to be met. So remember that both of these conditions needs to meet in order for us to be able to proceed. So I want to check for both. I'm going to divide by 0.2 here. And I get that n has to be at least 50. And then over here, I'm going to divide by 0.8. And this says n has to be at least 12.5. So in this case, because we need both of these conditions to meet in order for us to be able to have the large counts property meet, this is the one that needs to be true. Because if it's at least 50, it's also at least 12.5. So the minimum sample size is 50 sea turtles. If I only needed one of them to be true, then I would say, oh, well, then it would just be 13 turtles. But in the large counts property, we need both of them to meet. Okay, question 2 says, a reading specialist wanted to estimate the mean word length in a number of letters. So we're talking about means. For an elementary school history textbook, the specialist took repeated random sampling of size 100 at words. So that sounds like that is our n, right? And estimated the mean and standard deviation of the sampling distribution to be 4.9 letters and 0.15 letters, respectively. So it sounds like they're saying, hey, we know that... let's keep reading. Based on the estimates for the sampling distribution, which of the following provides the best estimate of the population parameter? So for the sampling distribution, sounds like we're saying this is the descriptor for the sampling distribution. So if we think about this, the mean of all the sample means is the same as the population mean. So in this case, we know the mean of all the sample means is 4.9. So our population mean is also 4.9. So I can cross out D and E. And then I'm going to do the same thing. We know the standard deviation of all the sample means is equal to the standard deviation for the population divided by the square root of n. So in this case, the standard deviation of all the sample means is 0.15. We don't know the population standard deviation, but we do know that the sample size is 100. And so that gives us 10 times 0.15. So that gives us 1.5 as our population standard deviation. So that makes our answer C. Okay, this one says the wingspans of a common species of housefly is said to have a mean of 15 millimeters and a standard deviation of 0.5. So it's saying the wingspans is said. So that means I'm talking about that is the population mean and that is the population standard deviation. Suppose a biologist wants to sample these houseflies and calculates the mean wingspan from each sample to create a sampling distribution of mean wingspans of this common housefly. What is the minimum sample size needed for this researcher to make a sampling distribution? So we don't know anything about whether the population distribution is normal. So to be sure that the sampling distribution for sample means is going to be approximately normal, we need to meet the large enough conditions. Because again, we're talking about sample means now. When we were talking about sample proportions, it was the large counts. So we need to make sure it's large enough. And for means, the large enough is saying that n has to be at least 30. So in this case, the sample size is 30 houseflies. I'm going to put at least, right, because it could be more. Notice how a lot of that information was not actually relevant to us. All we needed to know is that it was sample means. And we had to read closely. We did not see that the population was approximately normal, because if we did, then any sample size would have been appropriate. Okay, one last one for working backwards. So it says the dot plots below show the approximation to the sampling distribution for 3 sample statistics, A hat, B hat, and C hat, the same population parameter. If the value of the population parameter is 4, label each dot plot either as an unbiased or biased estimator. So the population parameter is 4, which means that if I look at where 4 is here. So which of these is an unbiased estimator? This one is unbiased because the mean of all the sample statistic A, we don't know what kind of sample statistic it is, but the mean of all the sample statistics for A is the same as the population parameter A. Whereas here, the mean of all the sample statistics for B does not equal the population parameter because it equals about 2, right? And then same thing here, it equals about 2. So again, the mean of all the sample statistics for C does not equal the population parameter. So as a result, the only one that is unbiased is statistic A, and the other 2 are both biased.